Alright, Chapter 8 is all about factors and factoring polynomials, but before we can factor actual polynomials, we have to talk about factors when it comes to just plain old numbers and then with monomials. So there's a rule that says that all whole numbers that are greater than 1 have at least 2 factors. So a number like 12 might have more than a number like 2. So factors of 12 are numbers that multiply together to give us 12. So we of course have 1 and 12, but then we can also do 2 and 6. And then there's one more possibility for this one, 3 and 4 also work. Those are factors. How about 10? 10 has not that many. It of course has 1 and 10. But then the only other one that it has is 2 and 5. A number like 2 is pretty boring. It only has 1 and itself. 1 and 2 are the only numbers multiplied together that give us 2. So for many mathematical tasks, such as simplifying fractions or finding common denominators, it's important to be able to factor a number, or to decompose it, to break it apart, into 2 or more factors. So all whole numbers greater than 1 are classified in 2 ways. They're either prime or composite. Prime means only 1 and the number are factors. So an example would be the number 2 that we just had. 3 is also prime. 4 isn't, because 2 can go into it, but 5 is, and then 7. Then the next one would be 11, and they go on forever. But the only stipulation is the only factor can be 1 and that number. No other numbers that multiply together. Composite means that it's composed of or made up of more than 1 factor. So composite numbers are all the rest. They have more factors. So an example would be any of these other numbers that we had up here. 12, 10, and we didn't do 25, but 25 would also be a composite number. So the number 1, it's one of those weird ones. Number 1 is neither prime nor composite, because prime means only 1 and that number are factors, and 1 is that number. And then it can't be composite because it's not made up of anything else. So 1 is often referred to as unique, or the multiplicative identity. And that should sound familiar from stuff that we did back in the day. So why are we doing all this? We want to factor our numbers down to eventually see what they have in common with other numbers. So we're going to do something called prime factorization, which means break up a number as much as you can until the only numbers that are left are primes. So number 24, we need to break that down. And you can start breaking this down in whatever way makes the most sense to you, except 1 and 24. That's not going to get us anywhere. And the way that I always do these is with something called a factor tree. So I split this up and say, what 2 numbers multiply together to make 24? And you could do any of them right here. You could do 2 and 12, you could do 4 and 6, you could do 3 and 8. I'm guessing most people thought of 4 and 6, so that's the one that I'm going to use. And then you double check to see if the ends of your trees are prime numbers, if they can't be broken down anymore. So the first end of my tree is a 4, not a prime number. That can be broken down into 2 and 2. And remember, you should always be able to follow your tree back up. So I broke the 4 down into 2 times 2, and then 2 times 2 would give me 4 if I wanted to go the other way. 2 is prime, so I don't need to go any further with the left side of my tree. I can't break down those red 2's anymore. But 6, on the other hand, is not prime, and that can be broken down into 2 and 3. Since 2 and 3 are both prime, I now have my prime factorization. And this means that 24 is the same as 2 times 2 times 2 times 3. And you can always test this to make sure that it's true. Type that into your calculator and you will definitely get 24. Try 60 and 19 right now on your own and pause the video. Alright, 60, I chose 6 and 10 to first break it apart. You could have done anything. You could have done 2 and 30. You could have done 3 and 20. Tons of possibilities. I chose 6 and 10, but either way you should still end up with the fact that 60 equals 2 times 2 times 3 times 5. Remember, you can always prove that to yourself. 2 times 2 is going to give you 4, times 3 will be 12, and if you multiply 12 by 5, you end up with 60. For 19, it's kind of a trick question. 19 is already prime. There's no two numbers that multiply together and give me 19, so I can't break it down at all. You could write 1 and 19 to remind yourself that that's it that goes into it, but that's not factorizing it. Alright, so the whole reason that we're doing this is to find something called the greatest common factor, or the GCF. So when comparing two or more numbers, the GCF is the largest factor shared by these compared numbers. It can be found using two different methods. I'm going to show you both for the rest of these slides, and then you can choose whatever one makes more sense to you or which one you find easier. So the first thing that we can do is go through and list all of the factors. List all of the numbers that go into both of those and find the biggest one that they have in common, the greatest common factor. Number 2 is what we just did on the other slide. Do prime factorization and see all of the numbers that they have in common. So let's list the factors first. And I find it helpful to list the factors in order. So the first factor is 1 and 30. 1 times 30 will give me 30. And then 2 can go into it 15 times. So there's no number in between 15 and 30, and no number in between 1 and 2 that can go in it evenly. And then the next one would be 3, and it goes into it 10 times. And then 4 can't go into it, but 5 can. And 5 can go into it 6 times. And then we end up with our two sets of factors meeting in the middle. So we know there's no other possibilities there but for 30 than the ones that we have up there. And then do the same thing with 18. So we have 1 and 18. And then 2 can go into it 9 times. So again, nothing in between 9 and 18. And then 3 goes into it 6 times. And that is the middle. 4 can't go into it, 5 can't go into it, and then 6, we're already back on the other side. So we want the greatest common factor, the number that's biggest that they both share. And they share more than one number. They both have a 1 in them, they both have a 2 in them, they both have a 3 in them, they both have a 6 in them. But we are only concerned with the biggest one. So in this case, 6 is my GCF. Some of you may have been able to see that before we actually did all of this work. If you can, awesome. But we're going to get to variables where it makes it a little harder. So the other thing you could do is use the prime factorization. So we could break up 24, which luckily we already did. 2 times 2 times 2 times 3. 2 times 2 times 2 times 3. And 60, which again we already did, which is 2 times 2 times 3 times 5. And then we want all of the factors that they share. So they each have a 2 and a 2 and a 3 in common. Now if we multiply all of those together, we end up with 2 times 2 times 3, which is 412. So the reason that we didn't include the 2 in the 24 and the 5 and the 60 is because the 60 didn't have another 2 and the 24 didn't have a 5 at all in it. So the greatest common factor between 24 and 60 is 12. And again, if you could see that before doing all that, more power to you. But here's the work behind it if the numbers get too big. What's wrong with it? So, algebraic monomials. So things that have x's in them, or y's, or z's, or any letter for that matter, we can still find the greatest common factor. I like to kind of do this with the prime factorization method, but once you get the hang of it, hopefully you'll just be able to stop and think about it. So find the GCF of 15 and 9. Let's just worry about the numbers, 15 and 9. The biggest number that they have in common, most people can probably see this, the biggest number that they have in common is 3. If you need to, write out their prime factorizations. 15 is 3 times 5, and 9 is 3 times 3. So what they have in common is 1, 3 each. So far my GCF has a 3 in it. And then if we look at our x's, the first one I have x squared, which is x times x. And the second one I have x cubed, which is x times x times x. So how many x's do they have in common? Well, they both have at least 2. So 3x squared is the greatest common factor for 15x squared and 9x cubed. It's the biggest thing that they both have in common. They both have at least a 3 and at least 2 x's. So now let's look at the next one. The GCF of 16a squared, 9b squared. So 16a squared can be broken down into 2 times 2 times 2 times 2 times a times a. 9b squared, that can be broken down into 3 times b times b. So if we just look at their numbers, they have no numbers in common. That's all right. Now if we look at our letters, they have no letters in common either. So in this case, the greatest common factor is 1. They do not really have a greatest common factor that's an actual number. But of course, if I multiplied 1 times this, it would be the same thing, and 1 times that, it would be the same thing. So if they have nothing in common, the greatest common factor is 1. Kind of a trick question. All right, break down 6x squared y, 4x y, z to the 4th, 12xz, and see if you can figure out the GCF. Go ahead and pause the video, and then when you start it back up, I'll have the answer up there. All right, so this is what you should have gotten when you factored them all out. So now let's see what things they all have in common. So they all have at least 1, 2. Some have more than that, but everybody has at least 1. Number-wise, no one else has anything in common. The 6 and the 12 have a 3, but the 4 doesn't. And then the 4 and the 12 have another 2, but the 6 doesn't. So no more numbers. So now let's look at variables. All of them have at least 1 x. So we're going to include that. The 6 has more x's, but no one else does. Both the 6 and the 4 have y's, but the 12 doesn't. And then both the 4 and the 12 have z's, but again, the 6 doesn't. So the greatest common factor between those 3 monomials is just 2x. And that's it.